So, we looked at classical description of these magnetic moments, and then that was sort of easy. You have a spin angular momentum, and then you get a precession in a field, and then you can describe this in rotating frame, and then you get the standard equation. And what we want to do now is a quantum mechanical description of basically the magnetic moment in a field, first DC field, then eventually AC field also, and then you should of course get back the same equations because it turns out to be correct finally. Okay, so first thing is what are the what are the eigen energies? So minus gamma h bar h naught and m. So so you have a magnetic moment mu, and then spin I, and then you will have m sub I as the possible values, and we are just writing m instead of m sub I just to avoid too many subscripts and all. Okay, and then these are the eigenvalues, and then the eigenfunction. So again with spin I and z component m is of course written as, you have some basis states. Okay, again we write that as u with the subscript I and m, and you're aware the time evolution is just e to the minus I e, again with the same sort of subscript e m t by h bar, right? So you have,
sir,
yeah,
this e is that e, right? The eigenvalue that you've written in the first.
yeah. So it's not looking the same. Yeah, correct. Yeah. So eigenvalues. So these are the basis states. So if you have spin half, you would maybe simply write it as u half and u minus half. Okay, those are the two basis states. And then the wave function itself, eigenfunction itself, has a time evolution which goes like this. And then in general, any system will be in some state, and that wave function is some linear combination of these eigenfunctions, right? So in general, the time dependent solution, this you are aware, so these form some complete set, and then you can write this as a summation over m, which goes from minus I to plus I. And you just do a sum over these basis states with some, in principle, some prefactors, unknown prefactors, right? So you C sub m, then u I m e to the minus I e m t by h bar. And these Cm's are some complex constants.
Sir, so can these constants be dependent on time?
We are going to work towards this, yeah. So, where to put the time dependence of the function and so on. Let me just work through this, yeah, so it will become a little bit more clear. So, at this point, all the time dependence is over here, and if you have a field, then of course, we'll come to that, it will become a little bit clear. So we are going to look at different descriptions, and so yeah, there will be some time dependence and all that. So you have a time dependent wave function, which is a linear combination of these basis functions with some unknown coefficients. Now, if you now just look at the, so you are going to look at quantum mechanical objects. So you are interested in expectation values. So let's say, so your expectation values so are written as usual. So for example, let's say you want to write the expectation value of the x component of of the magnetic moment. You are going to have dynamics, so there's some time dependence, and then you're looking at expectation value. So in general, you'll write this as, there's a standard prescription for this. So you'll have a psi star with the operator of this in between and a psi, and then you integrate over, so nominal volume element. In this case, it will be the various states, basis states. There's no sort of physical volume integral here. You're not looking at some spatial dependence. So it just, basis states are half minus half, so you're just taking care of the orthogonality of those and so on. Right? So you would, in principle, write this as psi star T, and then what is the magnetic moment, x component magnetic moment operator, psi of T, and then this is integrated over, so d tau is whatever, some volume element. So what we can do now is write each of them in their expanded form, right? So this is some linear combination of eigenfunctions which contain basis states and some time evolution. But for those basis states, we know what the orthogonality conditions are. Okay, so it's convenient to write this as some sigma over states, based on this. You have a psi of T here, so I can write down psi star, which will have a Cm star, and then instead of minus IE, you'll have a plus IE, and so on. So, yeah. All good? Or no bandage, nothing, it's just, okay, good. Yeah, so you'll just write these. So I'll just maybe quickly recap in half a minute. So what we are now going to do is, we have already done the classical description of magnetic moments in a magnetic field. So you get this precession motion, and then you can describe in, if you want a RF field, then you can go to a rotating frame, and then you can treat the dynamics as in some effective field, which is a combination of the DC field and some AC field. And then in resonance condition, the DC field goes away basically in rotating frame, and this just precesses about the AC field. Okay, that's the description in classical terms. We want to build the quantum mechanical description. So right now we are just saying you are looking at magnetic moments in a DC field. We'll bring in the AC field later. Okay, and then you just write the eigenfunctions as some time independent part, which will solve with this in the Schrodinger equation, for example, and e to the minus iet by h bar. And then in this case, we are just looking at the spin part. So this will have a plus half, minus half for spin half. Likewise for other spin values. And in general, the wave function is expressed as some linear combination of basis states where these are some complex constants which will eventually tell if you do a Cm star Cm, that will tell you what's the probability of finding it in the half plus half, and otherwise similarly minus half. Anyway, so then the next thing is, ultimately when you do quantum mechanical description, you want to look at what the expectation values are and how those are changing with time. So let's build that formalism. So here we have just written what the standard form for expectation value of any operator. And here now in psi star, you will write again sigma, Cm star, and whatever. Similarly, you will write for the wave function. So if you do that, and also, so you will of course, just to again, so this mu x component of moment, is just gamma h bar I x. So magnetic moment operator is related to the spin operator through a gamma h bar. Okay, and then you will put that over here, and then also we can write the matrix elements of Ix, right? You will get such kind of matrix elements. So this m prime Ix m, this is the short form for integral u star I m prime Ix u I m, and over some generic volume element. So watch out, we'll write psi star as a summation. You'll write psi as a summation. In principle, you should use a different index, right? The independent sum. So one is over m prime, the other is over m, and so therefore you'll get a m prime and a m.
So it is a similar idea of block wave function you are using in the Fidance method, that you're writing and it states ux.
No, nothing, no periodicity, no block, nothing. This is just a general form for the time dependent part of the. If u correspond to the eigenstate, then the time dependent is given by this. That's all.
Periodicity is not.
There's nothing, a single particle,
Okay.
right? So there's nothing about block wave functions here. No periodicity of the lattice, nothing of that sort. Okay, so this is a sort of short form where when you write the expansion, you will come up with terms of this sort. Okay.
Sir, won't there also be C m prime, C star m prime?
Yeah. So we will need to, yeah. I mean, but those don't need integration. Okay, so it's only this one.
The integrand part.
Yeah, correct. So just that part will be this. The other thing, some prefactors are there. Okay. So this is one point. So already from here you can recognize. We'll write that shortly. Which is that I plus is half. Sorry, Ix is half I plus I minus. Okay, and we'll need later. So Iy is 1 over 2I. I plus minus I minus. Okay, so our usual way of writing this raising lowering operators is I plus is Ix plus small I, Iy, and I minus is with the minus sign. And so the reason we are writing it like this is we want to evaluate these kind of matrix elements, right? So I will write the Ix in terms of I plus and I minus. You already know what's going to happen because I plus acting on m, that should give something m plus 1. I minus acting on m will give you some prefactor m minus 1. Okay, and then because of orthonormality of these states, you will get non-zero only if m prime minus m is plus minus 1. Okay, that's basically to take care of this point. So one rewrites the Ix in this form, and then in terms of precise prefactors, so you have I plus acting on U corresponding to nuclear spin I, and m sub I, which I write as m. So I plus acting gives you square root of I times I plus 1 minus m times m plus 1, and on the right side you have U I m plus 1. So this is the raising operator. Similarly, I minus is U I m. This is the lowering operator. So we have similar sort of prefactor I times I plus 1 minus m times m minus 1, and this will lower the state from m to m minus 1. Okay, and so what we want to do is basically evaluate this expectation value of x component of magnetic moment. So you are going to write this as a summation, okay, as well as the psi star as well as psi. Then mu is written in terms of I, okay, mu x in terms of Ix. Then recognize that the Ix can be written in terms of raising lowering operators. And then when they operate on m, they'll give some prefactor times m plus 1 or m minus 1 and so on. So you work through this, and so I'll just write, so I skipped a few steps here. So this expectation value mu x component with time comes out to be gamma h bar. and then within bracket you have, the prefactors are there, C star half, C minus half, and then you have half Ix minus half e to the minus I gamma h naught t. So this is one term, and another term basically containing complex conjugates. So C star minus half, C half, and then I have the other matrix element minus half Ix half and e to the I gamma h naught t. Okay, so this is just working out the algebra and writing in terms of the matrix elements, and then one step further is recognize what this is, writing in terms of plus and minus. So also, by the way, if you work out this thing here, this matrix element comes out to be half, and this is just the complex conjugate of this, so same thing. Okay, so overall, what you get again, I mean the lecture is recorded, so you can just work through this. You can then work through the algebra. What you get after doing this very straightforward algebra, it takes less than 5 minutes. What you get for x component of the magnetic moment expectation value is gamma h bar. I'll tell you what these are: A, B, cosine of alpha minus beta plus omega naught t. Okay, this is the general form of the x component of magnetic moment expectation value as a function of time. At each time it is different, so it has some oscillatory nature. What are these alpha, beta, A and B? It is just the definition of these constants. So the C half, you have these undetermined constants, prefactors to the two terms in the wave function. So C half and C minus half. So we are now dealing with spin half. Okay. So C half is written as A e to the power I alpha, and C minus half is written as B e to the power of I beta. Okay, so I've here not shown the full algebra, but what you have to do is you go back to this step, write the C's as some A, C half is A e to the power I alpha. So C half star is A e to the power minus I alpha. Likewise, you write C minus half. Likewise, these two things. Calculate these matrix elements. You can write in terms of the frequency. So this can be written as I omega t and so on. So that's what that omega is in the next step. And then just simplify. What you get mu x is something like this. Okay. So likewise, one can evaluate. So remember, we are dealing with magnetic moment. So quantum mechanical magnetic moment in a DC field, H naught. Okay. The RF will add in a bit later. So the rotating frame business, all that will be a bit later. Right now, just what's happening in a DC field. Okay. So X component has some time dependence like this. The Y component also you can work out similarly. You just do IY and then rewrite the Iy in terms of I plus I minus and so on. So if you work out, mu y just comes out to be minus gamma h bar AB sine of alpha minus beta minus omega naught t. Once again, I repeat, the omega naught is simply gamma DC field. You know, the standard, that's the precession frequency in classical motion. Here it is this quantity, gamma h naught, right? So you can, by doing these integrals, you can calculate the expectation value of mu x, expectation value of mu y, and expectation value of mu z. Okay, this is all in DC field, so mu z you might already expect it will come out time independent. So gamma h bar a square minus b square by 2. So in all these, there's no time dependence in the coefficient. The time dependence is just purely e to the minus iet by h bar. You know, the Hamiltonian is also time independent. It's just a constant field. So but when you go over to the final case where you have a RF field, then there's a time dependent Hamiltonian. Then we will see how to then transform now. Okay, so but right now we have now worked out what the expectation value of the magnetic moment is when it's placed in a DC field. Okay, so you get time independent z component of the moment and time dependent mu x and mu y, which looks familiar. Okay, so you can also, you will note, you do mu x square plus mu y square, right? This square plus this square, constant, right? So it's basically magnetic moment making some angle with the field, and the mu x, mu y are changing. There is a phase difference between the two, right? One is cos, the other is sine. So it's that motion, and the magnitude remains same of mu x square plus mu y square. So it's similar to a precession motion. So one can view this mu as making some angle. So one can, right? So this is time. The mu z is time independent, and one can view mu, the expectation value, as some kind of vector making an angle with respect to the applied field, with respect to the z-axis. So let's do a sort of direct comparison. So now forget this. Suppose you have a vector A, okay, and we have our usual right-handed coordinate system x, y. You know, just see what are the analogous quantities. You're looking at a vector A. So this is my A. Okay, it's making some angle theta. So you know, you're familiar. So with this, the z component is some A cos theta, and then the z component is A cos theta, the x component is some A sin theta cos phi, and y component is A sin theta sin phi, right? So you have a standard decomposition of vector in the Cartesian coordinates, where the angle with the z-axis is theta, and angle of the projection with the x-axis is phi, right? So Ax is A sin theta cos phi, Ay is A sin theta sin phi, and Az is A cos theta. Okay. What we want to do is we want to compare this. We have these decomposition of a vector in XYZ coordinates. We want to compare this with our mu x, mu y, mu z expectation values. Okay, can we recast the mu x in a form a sine theta cos phi, this one in a form a sine theta sine phi, and this one in a form a cos theta? And then we identify what that a is, what that theta is, right? So it's just some algebra. You can write this as some a cos theta, and then you can again write this as a sine theta cos phi, sine theta sine phi. So obviously the phi should have, this argument here. This should be like some phi, so that ultimately you will get, and this should contain some sine theta, right? And then ultimately this should contain, this is a cos theta, so this should contain some cos theta. Okay, so just a matter of algebra, and then you have some condition that this square plus this square is 1 and so on. So one can do that fairly easily. Okay, and then therefore that helps us rewrite our magnetization, single magnetic moment, expectation values, which then look like this. Just to draw analogy.
Theta should become 45 from the.
No, it's some general. No, it depends on alpha beta.
But the component of sine theta and cos. Okay. Oh, sorry.
Need not be, no? So,
the x and y sine theta.
You have some time dependence here. Yeah.
Sorry.
Yeah. So this fairly, again, 5 minutes, fairly straightforward algebra. If you do, it basically looks like you basically have to choose phi as minus alpha minus beta plus omega naught t. The reason is that in the mu y term, you do a sign, and then therefore you need a minus sign. No, overall, if you look at the mu y, you have a minus sign of something. So if I call this, if I take this as minus phi.
Or you can write omega t minus alpha minus beta. So omega t there plus.
Yeah. It's just a matter of working the algebra with this defined as something like phi, maybe minus phi. That's what turns out to be the convenient conversion. Okay, and if you do that, you can basically rewrite mu x, so there's a time dependence of course, as gamma h bar by 2 sine theta cos phi, mu y is gamma h bar by 2 sine theta sine phi, and mu z is gamma h bar by 2 cos theta, where mu is like a vector with magnitude gamma h bar by 2, vector with length gamma h bar by 2, and the angle is defined as, so phi angle is defined here, and theta, one just has to make a comparison with, you need to define theta, no? So with this one, so gamma h bar by 2, and then this thing here is basically cos theta, right? So this is cos theta. Then this looks like a cos theta, okay? And then based on that, you can try to write what is this. So gamma h bar by 2 I remove and put a 2 here. Yeah. So you'll have a 2ab, likewise you'll have a 2ab, and then you see, but then there should be this should be sine theta, cos theta. So you can just, and then there's a minus sign, etc. So you just need to work through the algebra. ultimately you can rewrite the mu as looking like a vector with its x, y, z components. Okay, so because ultimately you need cos square theta plus sin square theta is 1. So accordingly, if cos theta is a square minus b square by 2, you can write down what is sin theta. Okay, so just a fairly straightforward algebra. So I get, remember there is a time dependence here which is already there in the file. So anyhow, might as well write this. Okay, this is a time dependence here, and that time dependence is contained in this actually, the file. Okay, so there's a time dependence on the x and y components of the vector, but no time depends on the z. And then this looks like, straightforward. Mu is like a vector of length gamma h bar by 2, and it's making an angle theta with the z axis. Okay, and the x and y components are changing in a manner where the magnitude remains the same, and you have this sinusoidal variation. So it's precession of the magnetic moment, just like the classical answer.
So z component not depend on time.
Z component does not depend on time. Remember our classical picture also? I have a magnetic field, this precesses the Z component doesn't depend. It's only the X and Y which is like a sine cos.
But because of symmetry, rotation can we say like that?
Yeah, it's a rotation about the Z axis. So it's sinusoidal motion for the X and Y components. Time variation for the X and Y component is sinusoidal, off phase by 90 degrees, no? X and Y. Because the magnitude has to remain the same. So the length of the vector remains the same. Okay. Time dependence is only, this is cos and this is sine, so it's a pi by 2 off. So when mu x is 0, mu y is maximum. Okay. So it's like circular motion in the xy plane. So that's the precession we are looking at. So the quantum mechanical picture also gives you, thankfully, otherwise, the other way, quantum mechanical picture should reduce to a classical picture in some limit. So otherwise all these expectation values and you would be in a mess if the answers were totally different. Okay, so anyway, for the case of magnetic moment in a DC field, you get an answer for the time variation of the expectation values, which looks just like the classical answer. Then, it suddenly started, yeah. Maybe he came and looked and I don't know what he thought. So what we want to do next is write down the differential equation for the quantum mechanical expectation value of say mu x, mu y, mu z. Remember we have this equation governing dm by dt is gamma m cross h. Right? So we have, I was saying that classically we have this equation dm by dt is gamma m cross h. Quantum mechanically, what is it? Okay, so we obviously need to write down what is d by dt of expectation value of mu, and then are we able to finally write it as gamma mu expectation value cross h, and there we'll build in, once you have a RF field, what to do and all that. Okay, so we need to write down what the differential equation is for the dynamics, magnetic moment operator expectation value. Okay, so in order to do that, answer is clear. We get back the same answer. You finally get back d mu dt as gamma mu cross h. Okay. Obviously, you get back that answer, and so same as the classical answer if you think of the quantum mechanical problem and then think in terms of observables as the expectation values. Okay. So then one can put in the, so there are various things to do. First thing is we want to be able to obtain such an equation. This is one thing. So we already have expectation value of mu in terms of some integral, right?
Yeah.
So straightforward. No, mu x if you do, it's some operator ix sandwiched between wave function, complex conjugate wave function. We need to be able to write the time derivative on the left side because we want to do d mu dt. So likewise, right side we need to do time derivative and then see where that leads to. And then finally, I'm giving the answer in advance that we'll get an answer like this. So remember in classical case, when we finally wanted to look at the effect of the RF field, the AC field, we said it's convenient to go to a rotating frame because in that you can get rid of the DC field and the precession is about the AC field, which is then static in that rotating frame. So what is the equivalent of this picture in quantum mechanics? This going to a rotating frame and seeing then effective field and then the precession about the effective field and so on. What is the equivalent quantum mechanical? This also we'll be able to obtain. So what's the motivation now is to obtain quantum mechanical equations for the dynamics of the moment, which I've given the answer in advance, which will look like the classical answer. If you replace expectation value of this as the observable magnetic moment. And then the other thing we are exploring is, this is H is finally going to have some H naught plus some H1, okay, and that's going to have some time dependence, right? So, of course, odd vectors. And then, you know, how to view this motion. There in classical case, you go to a rotating frame. Here, what's the equivalent picture? Can we think in terms of rotation of a spin by some operator? Okay, that's what it's going to turn out to be. So that's where we are headed. Okay, so we want to take mu is already written. So for example, mu x is already written as some integral. Okay, psi star mu x psi. So then we want to do d dt. So we need to do a d dt here. So some algebra is involved where we are going to do time derivatives of things here. So in order to do that, some background is useful, which maybe in standard quantum mechanics you have done. So maybe I just quickly repeat the main result. So just let's consider some two wave functions, some psi of t and phi of t. Okay, this is one point. That these are solutions to the same Schrodinger equation.
So now we have applied the AC field.
Not yet. Right now, what we want to work out the algebra. You have a mu given by some integral. I want to find out what is d mu dt. Okay. Then in the Hamiltonian, I'll put in various things, whether there's a DC field, AC field. Right now, I just want to get a feel for how to do this time derivatives and what are the integrals, because there's a complex conjugate, the Hermitian, non-Hermitian operator. So some background is needed. So that's what we're trying to do.
Can we use Ehrenfest equation to finding time derivative?
I just give a few steps and write the result. So as I said, the background quantum mechanics, maybe some of you are already familiar. So that's very good. So you have this Heisenberg form from the Schrodinger equation where, you know, instead of putting the time dependence in the wave function, you put the time dependence in the operator. Okay, so that's basically where we are headed, but in a little while. Okay, so the background is this here. So these are wave functions which are solutions to the same Schrodinger equation, and let's say f is some operator, okay, with no explicit time dependence. Okay, then I'll write a couple of steps and then give the final result. So if you do d by dt of integral phi star f psi d tau. So we are not actually going to worry about some spatial dependence of wave function, etc. We're just looking at spin operators. So this is just the spin integral is over just the spin space. Okay, so you're not ever going to do an integral really, some r dependence or nothing of that sort. Okay, so this time dependence, if you have to calculate, this is what you will encounter, no, when you're doing d mu dt. Okay, so if you have to calculate, then f has no explicit time dependence. So you will just operate this on phi star and psi, and you'll have two terms, right? You'll have d phi star dt f psi, and then plus phi star f d psi dt. Okay, this is just some volume element. Okay, and then with little bit of algebra. Right, so this is clear, so this will have two terms. And let's see what they look like. So you can write that this d, left hand side is what we are trying to find out. D by dt of phi star f psi d tau. This is what we are trying to find out. Right hand side you have two terms. It turns out you can write this right hand side as I by h bar and commutator of Hamiltonian with this operator. Okay, I know very quickly how you can think this comes about. So when you take time derivatives, you'll have d psi dt, for example. Okay, but remember I h bar d psi dt is Hamiltonian acting on the wave function. I h bar d psi, that's Schrödinger equation, time dependent. I h bar d psi dt is h psi, where h is the Hamiltonian. Take the complex conjugate. Minus I h bar d phi star dt is Hamiltonian is Hermitian, so Hamiltonian acting on phi star. So right, so this is one term. Similarly, when you take the time derivative here, so these can be written as h times psi and h times phi, something of that sort. And then the order matters here, so one is f times h, other is h times f, and so on. So one can easily work out this algebra. You have probably done this kind of thing. So therefore you'll get a hf minus fh sort of thing. And the I by h bar is to take care of that Schrödinger equation. So this you get for something where f is time has no explicit time dependence. So when you're doing the time dependence in the integral, you have to take time derivative only of phi star and psi, not of f. So, but this gives you time derivative of say expectation value when these are those functions we have, basis states functions we have been looking at. Okay, so the notation is that this is written as df dt. F has no explicit time dependence. This is just a notation where you're trying to write down the time dependence of this integral. Okay, it's the matrix elements of f between phi and psi. Okay, that is written as df dt. Okay, that's the notation. So df dt equals I by h bar Hamiltonian commutator of Hamiltonian with that operator. Right? So now it's fantastic because if I want to do that operator is mu x, then my answer is h mu x. If it's mu y, h mu y. H is the Hamiltonian, by the way. And Hamiltonian you can then include first, if you want only a DC field, h naught. If you want finally AC field, you take care of that. right? So I can just put for f, I can put either mu x or mu y or mu z, then ultimately mu you'll write in terms of ix, iy, iz, and then I know how the Hamiltonian works with, Hamiltonian contains what? If you have just a DC field, it contains iz, right? Mu z, and therefore just iz. So,
But sir, we said this f is operator with no time dependence.
no explicit time dependence.
Okay.
Yeah.
Then mu x, mu y, like it's cost, so that's why.
No. So that operator has no explicit time dependence.
Sir, so is this like, should it be the expectation value of f?
Yeah, I mean it's expectation between, if it were the same thing, then it's expectation value, which is what we are driving at. So for us, this will be also be, it will be psi star f psi. Yes. Yes. So this is just a notation. I mean this is when, so again, I don't know, maybe one should put like phi psi, something like that. Yeah, it's some time dependence of the expectation value. Expectation value of the operator is when the phi and psi are the same, but this is just a notation, the time derivative of this integral. So that we are in short form writing as f. But agreed, yeah. Ultimately, what we have in mind is we want time derivative of the expectation value of x component, y component, z component. There we'll put this as psi star f psi.
Plus is partial derivative of del f by del t. And
But f has no explicit time
but
dependence.
in mu x and mu y it is.
No. The operator mu x has no time dependence. The expectation value finally has a time dependence. The operator has no explicit time dependence. Yeah. I mean mu z has mu x, mu y have ix, iy, iz. Right? Mu operator is I. It has no time dependence. So this is the picture we have where all the time dependence is in the wave function finally, but we can transform it in a situation where it comes in the operator. So
Different pictures.
different pictures, yeah. So we'll go to that in a little bit. For now, we wanted to get the equation for d mu dt in terms of say magnetic field. Okay, so with that in mind, we went to find out how to write this d mu dt, because mu is written, expectation value is written in some integral. I have to take time derivative. Well, I have an answer that each component, I mean for any operator, one can write the time derivative expectation value in this form. So I can do for mu x, mu y and mu z. So if you take mu z, okay, what is the answer? 0, because you will get iz, but iz commutes with iz.
Constant of motion.
Correct, right? So simultaneous eigenvalues. So d mu z dt is 0, of course. If this is doing this way, the z component doesn't change. Ix, iy, what happens? So f will have ix. This has, this Hamiltonian has always iz, right? I mean, other than gamma, h bar, etc. This has, in terms of the operator part, it has iz, right? And f, depending on if you're looking at mu x or mu y, will have ix or iy. You remember commutator of ix, iy?
2h bar iz.
Right, so it's some cyclic rule is there. So from with x and y you get z, and there's a I up front. Okay, so those are known. So okay, so when you have x here, so when you're looking at mu x, then you'll get iy in the answer. Right? So I mean so I'll just write down. So you will get iy, then you will get ix, and so on. So finally, what you get, so you're going to make use of ix, iy is I square root of minus 1, small I, right? And with cyclic variation, you can write the others. Okay, x, y, z, z, x, y, and so on. Okay, so when you now use these, what you get is, so by the way, Hamiltonian is minus gamma h bar, magnetic field Iz, Z component of magnetic field. Okay, we are right now just looking at a field in the Z direction. So once you put all that, then get the gamma, h bar, everything correctly, the dIx dt, right? So that's when the equation where you have mu x and then you take care with the h bar, etc. So you get gamma h naught, right? So I'm looking at constant DC field in the Z direction, gamma h naught Iy, right? This much is clear, right? Because when I'm taking time derivative for the, so psi star f psi, and then my f will contain Ix, so I'm mu x, so which is h bar Ix. So when I'm doing dIx dt, then I'll have Iz Ix here. So the commutator will give me Iy. Okay, so and take care of the gammas, h bar and all, you get dIx by dt is gamma h naught Iy. Likewise, dIy dt is minus gamma h naught Ix, right? So when you have x there, you have commutator of Iz and Ix, Iz and Iy, then that will give Ix. Straightforward algebra, nothing complicated. And the diz dt is 0 as we said, because the Hamiltonian commutes with Iz, right? Hamiltonian has Iz, that commutes with Iz. So this can be then rewritten as our earlier equation, classical equation. So you combine, you get di dt is I cross gamma h. Right? We looked at the special case, of course, where the applied field is along our quantization direction, constant field. But that's what it is, because for x component I'll get yz minus zy, so only the yz, and that's what it was. Similarly, y component will have xz minus zx, so you get that. So, and for the z component, I'll have xy minus yx, but there's no x and y component to h. So of course the z component is 0. So this correctly describes what we just did. And then you can rewrite in terms of the magnetic moments, isn't it? So you basically, so mu is gamma h bar I. Right? So I can then write d mu dt as mu cross gamma h. So we get back our usual equation that the torque, so if you have something with angular momentum, then applied field exerts a torque, and then the equilibrium motion is some precession motion, which is described by such an equation, and we get back the same equation. So now you just have to take care of the fact that you are dealing with expectation values of operators, and then you have the same equation. Okay, same as the classical equation. Now, next stage we want to deal with the effect of the alternating field, the AC field, right? So classical picture was that it's convenient to go to a rotating, because to view it in a lab frame, I know we can view it, but it looks a bit complicated. The time dependencies. So in the absence of an AC field, the moment is doing this. And when you apply the AC field, and let's say you are at resonance, if you're away from resonance anyway, it's a lot more complicated. But in the lab frame, if you apply an AC field in the x direction, then this angle increases, and that keeps happening until the AC field is on. So it goes in the other direction and then up and so on. Okay. So this motion, to view it in a lab frame, is obviously difficult. Just at resonance you can view it like this. Away from resonance it's not easy to picture what's happening. But if you go to a rotating frame, then the effect of the DC field, at least at resonance, is totally removed. You choose the right frequency, then there's no DC field. You just have an AC field, and if you're at the frequency which the AC field is going, then there's no AC field. You have a DC field. So for which you know the answer. So if it's like this, then the magnetic moment is just doing this about the AC field. So in a rotating frame, the picture is visually much more clear. Okay. So quantum mechanically also, we should see what's the equivalent. You know, here going to the rotating frame. Here, what's the equivalent? What does it mean? So let's now, so we want to look at presence of alternating fields. So let's see now if there's also an Hx, x component of the field, and of course time dependent. So Hx naught cos omega t. Okay, and right, that's what we actually want, that the field is pointing in one direction, but its magnitude is changing sinusoidally. So maximum decreases to 0, negative again decreases to 0, in that fashion you want it. But in terms of working out the equations, remember earlier there's this rotating frame business. So rather than looking at a field which is linear and then just going increasing, 0, decreasing, etc., for the mathematics, it's convenient to view a field which is rather doing this way. Okay, rotating field rather than this AC field. It's convenient to view a rotating field, because then when you go to a rotating frame, you know, it can be static and all that. But such a field can be generated by two rotating fields, one rotating this way, other rotating the other way. Okay, right? So one field, right? One is going this way, other is going this way. So when they are like this, you get full magnitude. As they go this way, it decreases, becomes 0, and in the other direction again it builds up, increasing, and so on. So one can generate such a field as a combination of one HR, which is given by H1 unit vector I cos omega t plus unit vector j sin omega t, and another one H left, which is H1, and so all the time dependence over here, that this H1 has no time dependence, I cos omega t minus unit vector j sin omega t. Okay, so you can easily see that one can combine these, right? Just add them and you'll get a 2H1 cos omega t. So, and also it can be shown if you are close to resonance, it's really one rotating field which contributes, the other one doesn't contribute to the final dynamics. Okay, so it's okay to consider this as just arising from these two fields and finally only one of them. Okay, so I mean just this one. So we are wanting to explore the dynamics of these moments in a DC field plus an AC field of this sort. Mathematically, it's easier to picture what's happening rather than a field like this, which is basically, pointing always in the same direction, and the magnitude increases, decreases, becomes negative. Rather than that, it's easier to picture what happens when the field, instead of this, it actually rotates. Okay, and it turns out it's a combination of these two, but finally you can just leave out this part when you're close to resonance and just work with this one. Okay, so we are just going to replace our applied field by H0 plus HR rather than H0 plus Hx. Okay, so we have the magnetic field as H0 along the k direction plus our H1. So H1, and then you have a I cos omega t plus j sin omega t. Okay, and then your d mu dt you can write down. You can argue that this now looks like mu cross gamma H0 plus H1. Okay. Not immediately obvious, but think through it. See the algebra we have
Can
done.
you repeat why you have taken just HR, not HR?
Yeah. So the argument is that in reality you want just this field.
Huh.
In terms of working out the mathematics, so this field means it's pointing in this direction and sinusoidally the
We
amplitude.
should take HR and HL also, no? So that.
Correct. So it's really Hx t is actually HR plus HL.
Huh.
Okay. One rotating one way, other counter rotating.
Yeah.
In practice, near resonance, the effect of this in the equations turns out negligible if you are near resonance. So we say that we just make these two basically the same. Okay, instead of the required field, we just put HR, not leave out the HR.
Sir, but how can we sort of physically picturize this? And why would HL not be so important near resonance?
In the sense, you are 2 omega away from, one is going this way, other is, with respect to the other is 2 omega off in the other
They
direction.
are out
So,
of phase, these two, HR and HL.
So, but if you are at going, so I mean, one is going omega this way, other is going omega this way. So if you are in a, again classical, if you are in a rotating frame with 1 omega, the other one is going at 2 omega. So in that sense, its effect is minimal. One can think of it that way. In terms of the, the torque is, I mean, you're looking at a resonance condition. If you are 2 omega off, you are far away from resonance. So it's roughly in that way. Okay. But yeah, ideally one should put both of them and then see what it gives. If I remember right, there is, I think Abraham
In
gives
resonance
it
means
that
it's always in most of the cases. When we are doing it's in resonance, right?
Yeah, near resonance, so it's negligible, but the effect has been demonstrated. I'll check. In Abraham, I remember he says it, right? There'll be effect at 2 omega, and that is demonstrated in some experiment. I'll check and tell you. But so yeah, you're ignoring it. I think there is a demonstration that this is also seen in experiment.
So can you say like why there is this 2 omega thing?
Oh, if you look in your usual rotating frame picture, so RF field is going at one part omega this way, another this way, in order to generate my AC field. So in the usual picture, I go to a rotating frame. Also, I'm sitting on the HR. Okay. So in that, I see my HR as time independent. So, but the other one I'll see going at 2 omega in the opposite direction. No? That's all.
The relative angular.
Relative angular velocity. That's all. So, yeah. So we get this sort of equation, and then remember now we need to see what happens. This I'll do next time. That how to now. So you remember in classical picture what we did is d mu by dt in rotating frame, how it relates to any vector, time rate of change, how it relates to inertial frame. There's a omega cross vector, that term appears. Okay. Now we are doing quantum mechanics, so there's nothing like rotating frame. How can now we redo this such that similar physics can be again obtained? Okay. So
So this one is total field or just anything?
this is total field.
No, above. H.
Total field.
Total field.
Yeah. So
for
DC
the
field.
RF, we just consider the HR.
Yeah. So actually it should be hx0 cos omega t along whatever direction, but we are writing it in this manner. Again, for some convenience. So this maybe, so now we need to picture what happens in quantum mechanics in terms of rotation of operators, rotation of moments and all that. So this maybe I'll do next time. If Wednesday is also okay, I'll
Sir, Wednesday.
next Wednesday we'll do.
Friday, I'm not there.
Friday you're not there. So anyway, Wednesday we'll do.
Okay.
We'll decide what we do after that. So next Wednesday again, 11 o'clock.
Yeah.